Thank you very much. You may wonder what is wonder of sine-Gordon system, but that's the whole subject of my talk. This is based on a joint work with Salvatore Stella, and I want especially mention that he is a last PhD student of Andrei Zerevsky, and he very recently defended his thesis. Okay, and also I want to mention that he also collaborated with me to prepare this talk, and he wrote a lot of, you will see later, a lot of beautiful figures, and it was created by him. I can't do that. And also, Andre and I together spent 1 semester in our last year in MSRI, and among also other participants who's here. And I made an announcement of this work before publication in a seminar in a MSRI. It was December, and after the seminar, Andre came and he honestly told me that he is not satisfied with my talk because I didn't even give a definition of a sine-Gordon Y system. Now I understand why he was so unsatisfactory about this after Sergei's comment in this banquet. Anyhow, so I said, okay, next time I'll give a more good, better talk in your workshop, in this workshop. And then he smiled, and that's good. And basically that was the last conversation I made with him. So I really had to prepare this talk to explain this subject to him. And unfortunately, he's not here, but I pretend that he's here and maybe sitting next to Sergei. And so I will explain what is this. And I have to use this slide by necessity. And but the PDF file of this talk will be available at my website after this talk. Not now, but so my goal is to try to invite you to download this PDF file. Okay, so let me start. First, just give a brief summary of my talk. So, sine-Gordon Y system (SG) here are some very complicated system of algebraic functional equation introduced by Roberto Tateo. He's an Italian mathematical physicist in 90s. And they originate from the sine-Gordon equation, which is a famous soliton equation. To be more precise, there are two subfamilies, sine-Gordon Y systems and reduced sine-Gordon Y systems. Both are associated with continued fractions. And my message of my talk is there is a wonderful interplay among continued fractions, sine-Gordon, reduced sine-Gordon Y systems, triangulation of polygons, and cluster algebra of types A and D. And I also want to mention the since the sine-Gordon equation is associated with affine, SL2 is the simplest affine Lie algebra. And so this whole thing should be a tip of iceberg of some gigantic thing, which I don't know what it is. Also, this remark is important. Don't be discouraged by the horrible appearance of the sine-Gordon Y systems, since they are beautiful in nature. So here is a plan. I have 3 sections. First 2 sections are introductory part, and we see this is a horrible part. And in the third section, we see the beautiful part. This fourth section is appendix, and I don't show you today, but you can see it if you download this PDF file. Yes, there's some incentive. Okay, so let me start. Before, maybe Andre didn't like it, but before giving a definition, it will be useful for some people to have a background. Okay, so sine-Gordon equation is such an equation. this is a deformation of a much more famous Klein-Gordon equation. This is just a fundamental equation for bosonic field. And since this so-called mass term, linear function is replaced by this sine function, some word playing, it is called sine-Gordon equation. This is good for Gordon, right? But a little bit pity for Klein. Anyway, this equation is important because it is integrable, also having solitons. And more recent, more modern terminology, it is a affine total field theory associated with affine SL2. Why? Because if you write it in a Lagrangian form, this sine becomes cosine. Cosine is a summation of two exponential terms. One is plus and minus in exponents, and they correspond to the simple root of affine SL2. Okay, so you can quantize this bosonic field. It is called sine-Gordon model. And after that, still it is integrable. And you can somehow, using physics idea, calculate the exact S matrix. And it has a property so-called factorizable. And this was done by Zamolodchikov brothers. And this work made these twin brothers famous in 1978 or something. Then Tateo in 1995 applied a so-called thermodynamic Bethe ansatz method for this sine-Gordon S matrix. This is a very important method contributed by many, like Yan brothers, Takahashi Suzuki, Wadayuta Hatajan, and so on. And schematically, we can explain the situation as follows. Starting from this sine-Gordon S matrix as an input, you can somehow make an boil up and put some spice and give some voodoo and so on, and you get some integral equation. It is called a sine-Gordon TBA equation. It is an integral equation. It's usually impossible to solve it explicitly. But instead of solving this equation, if you find have a solution of this integral equation, it turns out that this is also a solution of more simple algebraic equation. This equation is called Y system. This is a Y system we are going to consider. Also, I want to mention that there is so-called coupling constant here, beta. It is conventional to consider the following parameter C. And it's important to distinguish whether C is rational or irrational. Then the model becomes finitely closed or becomes infinite. You need an infinite particle and so on. So rational case is very important. And that's why, in this way, our rational number or continued fraction enter into the game. And especially we concentrate on this region, so rational in between 0 and 1. So what I explained is sine-Gordon and RCG Y systems depend on the continued fraction expression of C. So very, in summary, what so far, broadly speaking, the sine-Gordon equation, sine-Gordon S matrix, and sine-Gordon Y systems are like cow, milk, and cheese. So milk is produced by cow, cheese is produced from milk. But if you compare cow and cheese directly, it's very different. So if you compare this sine-Gordon equation and sine-Gordon Y systems, they are totally different. It's not just a discretization of this one. Okay, so this is a rough idea. And now I have to go into some more precise definition. I have to start from continued fraction. So somehow it's convenient to give a parameterization of a continued fraction in this way. It's opposite to the convention from of ordinary one in one, but we start from this one. So
the rationality of psi
yes.
from the point of view of,
Yes.
let's say, Liouville theory, something like that, what it amounts to?
Why it is important? It is, that's a good question. Yeah, yeah. So it is important when you consider the quantum theory. And then you want to consider the spectrum of this quantum theory. And well, if it is irrational, so if you had your elementary particles, and eventually you end up with the composite of it and have infinite number of particles. However, if it is rational, you can cut it. Yeah. So rationality is a finiteness property. So that's why we have some nice equation. Okay. So by this expression, it's a continuity fraction is just the sequence of integers, and we can have a parameterization of a rational number in between 0 and 1. Okay, so for each sequence of integer numbers, we have also have a family of continuity fraction just by cutting this continuity fraction at certain level. So for example, so in this way we have not only one fraction but also several fractions, just cutting here, cutting here, so on. And so each fraction can have a reduced expression, and you can add these numbers, and you have some numbers. So in this way, from your input, you can get several numbers. I'll give an example. So this is our running example. Suppose f is 3. So f is I called this a generation, and if only 3 generations, like 6 for 3. The first generation is 1 over 6. Second, this number. And you have such sequence of integer. Also, you can add this number. You also another sequence of numbers. We will see this number later. And particularly, we use this number P1, P2, P3, in this case 1, 6, 25, to define the Y system. So Y system use this input. And it is well known that they satisfy the recursion relation. And I want to say that all the nice properties originate from this recursion relation. So continued fraction is responsible for this. Okay, now it's time to introduce first, reduced one is a little bit simpler, so I start from reduced sine-Gordon Y system. So input is just this sequence of integer. I mean, this is just a continued fraction. Okay. So by technical reason, we assume and 1 is greater than 3, but it's not so important here. So we define a Y system. It is a functional, algebraic functional system of infinitely many variables. So this is a variable which we call Y variable. We have 3 indices. U is called spectral parameter, which is just an integer. A here runs from 1 to f. It is called generation. M depend on which generation you are considering, and it is summarized here. For each generation, we have some number. Only for first generation, we have to subtract 2 by some reason. Then we just put it in this way, just in diagram of type A, like this. Also need some convention of sign. So A is even, odd, then it is just 1. Odd, then it is just minus 1. Now, this is a general equation for each AM except for 2, 1, 3, 1, F1. We consider a family of functional relation. Here we have an input, this integer PA coming from continued fractions. And also we have some signs, and we have tilde. Tilde means BK here is adjacent to AM in this diagram. So this is just at most only 2 terms in the right-hand side. And if your generation is 1, we don't have this portion. Everything this is just 1, and that's it. And it is a classic Y system type A. But we have some other things here. So this is some descendant. Okay, so this is a general relation which is not so ugly, but exceptional relation is somewhat horrible. So when AM is 2, 1, we need ask this relation. For those numbers, we have to ask those relations. Take a look. I give some moment. You have some impression for that. Maybe not, right? After 15 seconds, you don't feel anything. It's like a kind of modern art. You don't see anything good from this equation itself. Me too, and everybody except for Tateo. So in that way, this equation is become forgotten in a sense because no way to deal with such equation. So summary so far, it is our SGY system is very complicated, but nevertheless is a generalization of Y system of type A. Okay. At least one can say the following. This Y system can be cut into two parts, decomposed into two parts by parity. So if for each Y is a set of all Y variable. For each AMU, you can calculate these things. We may call this parity of this variable. And whether it is even or odd, or you can decompose it. And it is not difficult to see that each relation of the Y system involves variables only from Y plus or only from Y minus. So you can safely separate these things into two parts. So the Y system is bisected into the one for Y plus and one for Y minus. Especially one can concentrate on the Y system for Y plus, for example. Now, sine-Gordon is very similar. Just I mentioned the difference. Now we, instead of type A diagram, we replace it into type D diagram. So by adding 3 terms here. So 3 new indices are added. Otherwise, very similar. Then we consider a general relation. But now this adjacency is with respect to this type D Dinky diagram. So if particularly you choose this one for left-hand side, then we have 3 terms here. Otherwise, it's very similar. So, sorry, I want to say that. So it means if there's only one generation, then it is classic Y system of type D, originally introduced by Alyosha Zamorochkov. Okay. And so this is an expression relation, and we add some term here. And here it is exactly the same form as the type A case. Again, this also we extend from not 1 but 0, but still it doesn't matter to you, right? Not so much, right? So it doesn't change the situation so much. Anyway, this is a Y system type D. And the reduction means at this sine-Gordon Y system, if you have this extra 3 variable which we had to be some constant, -1 and 0, it's okay to do it. Then you get reduced sine-Gordon Y system. That explains the name reduced. Okay, so basically it finishes the definition of Y systems. What is the use of this Y system? And now next I explain Tateo's conjectures. First, general philosophy is as follows. So, in general, this S matrix model, not only for sine-Gordon, but there are several many, it is a massive theory, means that particle has some mass. On the other hand, two-dimensional conformal field theory is a massless theory. And there is a strong belief that this integrable S matrix model and the conformal field theory are related in the following way. So taking a massless limit, you get conformal field theory. From conformal field theory, you consider some massive deformation and get S matrix model, and so on. So these two things are related by this. This is philosophically okay, but something is very, very difficult to prove it by mathematics. It's beyond the region of mathematics. But suppose this is true, and TBM method is somehow giving some evidence for such connection. Means that, as I mentioned, by TBM method, we have a Y system. What is the use of Y system? Y system is a tool to extract some essential information of conformal field theory limit of the S matrix model. And what we expect is the following. Y system created from this in this way should have a period. And this period represents the conformal dimension of the deformation field in conformal field theory limit. Well, no, it's not. Conformal dimension is some rational numbers. Yeah. Period, but from period you can calculate it. I mean, Y system has some normalization. So if you normalize, then it becomes an integer. But to really compare with conformal field theory, you you need this modification by normalization, it usually becomes a rational number. It is a rational number. But you can get it from this period. Next, Y system are supposed to have a dilogarithm identity. And this dilogarithm identity calculate the central charge of conformal field theory. These two information is essential to determine the possible conformal field theory. This is rational number.
The coefficient pi square over 6.
Yeah, if you so this is rational number. So this is called rational conformal field theory. Everything is rational and finite. I mean, finiteness of the theory. Okay, so this perspective leads to several conjectures on the periodicity and dilogarithm identity for various Y systems coming from this S matrix in 90s. In particular, Tateo made, it's natural to make a conjecture on explicit formulas of period and dilogarithm identity for his Y system. If he didn't make it, it's rather useless to introduce this Y system. This is the whole purpose of introduction of Y system. Okay, so now I'm giving his conjecture. First, periodicity. So remember that Y system is associated with a continued fraction. We have a reduced expression. You can add some numbers. Well, Tateo's conjecture is as follows. The reduced single Y system has a following periodicity. Just twice of this number is a period. That's it. For sine-Gordon case, a little bit complicated, but if depending on this parity of RF, it becomes a full period or it becomes a half period. And so the tail of thinking may exchange if this number is not. But if you multiply this, then it becomes full period. Oh, this is not important. The point is twice of this number is either full period or half period. And he said in his paper, at that time, this physics paper never used the word conjecture. So he said the periodicity property that can be numerically verified with high precision. It means you can put some numbers and see periodicity. That's it. Numerical verified. Yeah, of course. I mean, even a single case is even enough. I mean, just take a random number, and if it is periodic, there's no chance if the original function is not periodic. Okay. Anyhow, but it is a conjecture. Next conjecture is a dilogarithm identity. So let Lx be the Rogers dilogarithm defined by this integral. So his conjecture is as follows. For any real positive solution of Y system, that complicated system, and assume this is already periodic. So then Y plus is a Y variable of even parity, and we concentrate on this fundamental region of period. So there are only finitely many numbers. So this is just finite sum. You can calculate this. This gives some number. Usually this is just some irrational numbers. But if you divide this 6 over pi square, he said, okay, this is some rational numbers. And moreover, he gave this explicit conjectures. And once again, he didn't say this is a conjecture. He said, with an appropriate number of initial condition, we find the following identities. It means, well, it's possible to make a numerical calculation of this. And so since Y system is actually a recursion relation, if you consider this spectral probability as a discrete time, you can start from some initial condition and put any number, and you can calculate it. Then you see well, multiplying some number, you get actually integers, and yeah, actually this is integers, and so, but it's actually amazing that he made such a precise expression having some several variables. Okay, this is good, but this one is not so easy. But he made conjectures. Turns out, NA is the original input of these numbers. Yes. Anyway. Yes, because this is a recursion relation. If you just take a positive number for your initial condition, then everything becomes a positive, because Y system is a positive relation. So anyhow, this is the most complicated example of the dilogarithm identity arising from the TBA method. Remember that the complexity of the Y system, and you have such formula. There's no other. I've never seen such things. Anyhow, now, okay. Amazingly, 1 year later, Tateo and Rioch solved one conjecture. That is the periodicity for reduced sine-Gordon model. How did they make it? They construct an explicit solution. Explicit solution by cross ratio. And so it was a work by Rioch. Actually, this is misspelled Rioch and Tateo, 96. So let's just define cross ratio in this way. And we introduce formal variable of Zn. So it's infinitely many variable. And assume the periodicity of this variable. Only assuming this, then we have the following solution. So y, you just consider formal variable given by this, where this inside is given by some equation. You don't have to look into this, but it's some linear relation for this u. Then they said, it is straightforward to verify by direct substitution that the general solution of this Y system, reduced Y system, is here. Well, how did they reach to this solution? I think I can explain it. First of all, their target is not this Y system, but a simpler one, type A case. And now we know that this type A is related to these polygons. And we know that this is described by this cross ratio. Anyway, that was their the first obvious explicit solution of Y system. And since this RSG Y system is a generalization of type A, they actually try to extend this to others. And then maybe it's not so much difficult to have such things up to some constant because general relation of Y system is such form. Then they just plug in and surprisingly found that with some choice of constant, it really satisfies a more complicated this exceptional relation. That's my expectation. Anyway, since this z is a variable which is periodic, and we have u, actually have this 1/2. So everything is periodic if we shift this u to twice of r, because this is cancelled by this, but we have this periodicity. So the periodicity is proved. Now let me give other known and related results on Tateo's conjecture in a chronological table. So this one, what I explained, periodicity of RSG is proved. That's good. Also, Frenkel and Senesh, 95, proved dialog identity for type A1 system. Type A corresponds to RSG for F equal 1. But that's good for startup, but now then after that, it stopped. Because there is no systematic method to prove these conjectures. If there is no introduction of cluster algebra in 2000, the situation does not change so much. But of course, this happened, and then of course BC is before cluster algebra. Okay? So this is a situation in BC, but it's naturally called after this AAD, and the situation changed, and gradually recognize that cluster algebra is really the key source to prove these things. In other words, without this, it's still. Please consider something and tell me what I should. Well, cross ratio is some other. Anyhow, so first improvement was the proof of periodicity for type D. Also, they did it for type E, but this is particularly sine-Gordon for f equal 1. That's good. And then the Frederick-Chapoton used this result to even prove dialog identity for type D case. So, in a sense, so together, f equal 1 case finished. But then, then I also, Kera and also I also get into this business, and similar conjectures for another Y system, it is called RSOS Y system, were proved by kind of a new method called tropicalization and categorification method in the cluster algebra. And after that, it's natural to tackle with this most complicated Y system and for Tateo's conjecture. And together with Tateo, I try to solve this for f equal 2 case, next complex example. And this method just worked out. So we proved f equal 2. F is the length of the integers for continued fraction. So level, so generation. So, okay. Well, however, the extension of this analysis to general F seems not easy because analysis becomes too complicated. In a sense, we solve this equation at tropical level very explicitly. I can do it for 4 equal 2, but for F3 and 4, I found that the situation is really difficult. So again, we are stuck. And the source of problem is, as I mentioned, we don't see any good structure in these Y systems. But now, today, I want to happy to tell that our main theorem is with Salvatore Stella is Tateo's conjecture is now fully solved in full generality. What happened? All right, now key idea is using polygon realization. This is really the key. And so I mentioned that the referee of our paper pointed out that we use cluster algebra method, but we didn't recognize that the cluster algebra there is actually a type A and D. Okay. But on the other hand, it is known that the cluster algebra of type A and D are realized by polygons without for type A and with puncture for type D. For conjectured, for Shapiro, and so on. So, of course, these two things, I know it, but I never combine these two things. But it's important to combine these two information. So, we may try to realize a Y system for general F by polygons. This is actually possible, and it turns out the nature of Y system becomes most apparent in the polygon realization. Okay, now we are going to the best part of this talk. First, I recall you a Y seed of cluster algebra. So a fixed positive integer n. Start from initial labeled Y seed, which is a pair B and Y. B is a skew symmetric matrix of size n, which is called initial exchange matrix. And Y is an algebraically independent variable, Y1 to Yn. It is called initial coefficients, but I want to call this simply Y variables. The mutation rule is as usual for B, and this is for Y variable. And we can repeat the mutations and obtain a set of Y seed from your initial data. On the other hand, let's talk about labeled triangulation. So, well, this already explained in several talks. I can skip. So we have a labeled triangulation, and you can make a flip, and you have. So important fact is now we stick on this label. Now, polygon let me explain how one can realize these Y seeds using a polygon. So we associate a Y seed by to each labeled triangulation of polygon as follows. The matrix B is if you have a triangle like this, and if you have an angle from I to J in this way, then we attach this number. Otherwise, it is 0. And then a Y variable is defined in the following way. For the initial triangulation, attach the initial Y variable yi to the diagonal I. For the labeled triangulation obtained by mutation, by flip, k, we attach the y variable in the following ordinary mutation rule, actually. Then, in this way, you can attach each rebel triangulation a new y seed. We have a one-to-one correspondence for such, but one thing is not obvious. I mean, if you make a flip and get some triangulation, but there might be other ways to get the same triangulation. If you define this y seed in this kind of recursive way, it is not guaranteed that those two give the same answer. But it is true. There are at least two arguments. For example, one argument is you can identify this y using hyperbolic lengths of some. Okay, I don't explain much, but using hyperbolic geometry. Other way is using a tropicalization technique, and this actually calculates the so-called C vector, and the C vector actually determines the y variable. So you can do this, and this method is also work for even having punctures. Okay, anyway, so it means you can forget about y seed, but you can safely work on Rebel triangulation. Okay, now let's work on to prove the periodicity of y system using this method. First one is a classic case, but nevertheless, I will explain it. So consider the sequence of number, just one length is n1 is 6, and this is a data, and summation gives you a 7. So 14 is the expected period of y system. How we get it? So this is a linking diagram. We have 4 variables, and this is a relation of y system. This is a classic y system of type A4, which is realized by 7-gon. And 7-gon, we take the following initial Rebel triangulation. It is just a zigzag triangulation. We give a Rebel 1, 1, 1, 2, 1, 3, 1, 4, which correspond to the, this Rebel of corresponding y variables. We make a mutation in the following way. If we first make a mutation for this encircled arcs and make a flip, you get this. Then alternatively, you make a mutation for this and make a flip, and you get it. After 2 steps, you get a rotation by 1. And so it means if you make this 7 times, I mean after 14 steps, you get to the original one. So we have a periodicity of 14. And later we call this point as forward mutation point because this diagram moves in a forward way. I just prove that the y variable attached to this one, I mean a small y variable attached to this one is periodic by using this geometric method. But we have to identify this with our y system. Identification is as follows. We have a y variable cluster algebra at each time. And I will identify this with this capital Y variable for y system only at the forward mutation point. And then in that way, we obtain the y variable for belonging to y plus, the y variable having a positive parity, even parity. And the statement is they satisfy the y system for y plus. For example, how we get to obtain this one? Let's look at this arcs with label 1, 2, and this is the forward mutation point. So this is this red means it corresponds to the forward mutation point. Make a mutation, it is inverted. So, but next one is not a forward mutation point. So we cannot identify this with this variable. But now we make a mutation for this one, and which is adjacent to this one. So this gives you the following contribution to this y12. And this y12 becomes forward mutation point again. So we have an identification with y variable. So if you change this y to y, then you obtain this. So what I said is this y system is just embedded into the relation of this small y variable in this way. So in fact, this is it. I mean, this already proves the periodicity of y system with period 14. We don't actually solve anything, but we just formulated this y system by this triangulation. And that gives you the proof of the periodicity. Because instead of writing some expression, we have an explicit solution by triangulation. I want to do this method for further complicated y system. So now next one is more important. So 6-4 case. So f equal 2 cases. Continued fraction is such numbers, and we add up. We have number 31. This is the number of. So we consider the triangulation of 31 gon to give a proof of this periodicity. I recall you. Okay, so it should be multiplied by 2. So 62 is a period of y system, expected period. So I recall you. This is a thinking diagram. We have two kind of y variable: first generation and second generation. And we have a relation and such kind of unclear relation. Now, since this system was already solved by Tateo and myself by the Quiver language, what we need to do is just translate this Quiver result into triangulation of 31 gon. And having that, I found a very surprising fact. I mean, so this is the initial triangulation. And this is the forward mutation point. And key observation is the following. If you make a mutation for these 2 points, this one is flipped, this one is flipped. Others are stable. But as a result, we have a reflection with respect to this one. I mean, this is important. I mean, other points are either symmetric or just did not cross to this one. So this is symmetric. But this is not a symmetric with respect to this, but it is flipped. So it gives a reflection. After reflection, you get this. You just read. Now, next forward mutation point turn out to be these 6 points. And if you look at it, if you really flip this, what you get is, again, the reflection along this new axis. So what I mean is each mutation is a reflection with respect to certain axis. But, if you make a reflection twice, you get a rotation. And in this case, rotation by unit 5. So unit 5 is good because number 31, okay, it's a prime number, but the fact is 31 and 5 are coprime. So each 2 step, we have a 5 rotation. So you have to make a 62 mutation to come back to the same figure. So this is a period. Okay, so what I said is periodicity is just realized as the full rotation of this diagram. To be more precise, this is a period of unlabeled triangulation, and it is not a period of labeled triangulation. The label is shifted. But it turns out this is not a matter, so you just forget about this comment. Okay, but we have to show that this really realized the y system. We know that this is true, but let's check it. How this complicated equation coming from this. And so I think this slide is the most important part of my talk. So let's see it. So we wanna interested in the mutation of this 2-1 is the target arc is here, and it is flipped at time equal 1. So after that, it is flipped, and also your y value was inverted. So I wrote it one time ahead, and this is a result after the mutation. And after that, we have the following diagram, and these are the mutation point. And so because that this is our target diagram, and we have a mutation at this 1, 4, and so this contributes to this line by this factor, because this is anti-clockwise, And so we have such factor. And we can repeat this. And next time, this 1, 3 contribute to this. Other mutation is irrelevant to this variable, but this is shares the same triangle, so we have this diagram. And we do time 4, again this one, time 5, again this one. Now, time 6. There's a mutation, but this doesn't share the same common triangulation. So this does not appear here. Time 7 is interesting. There are two diagonals which is adjacent to this one. One is counterclockwise, giving this contribution. This is clockwise, so this gives this contribution. And so on. So time 8, time 9, again here, time 10, time 11, 13. And after that, 13, it is again flipped. It means it have a new name, but these compiled kind of influence from the former mutation, and this identifies with this. This is a Y system. So this explains this unknown equation just by is just reflecting this rotation. Maybe you may want to see it once again, hopefully. So maybe you just look at the inside of it. This is the first generation. Inside is rotating when you make a rotation, but outside is somehow stable. It's interesting. And this explains. So this is a secret. So in reality, okay, so this is just a disguised form, and if you really want to write down your equation, it looks like so, but this is a reduced sine-Gordon Y system, which is, I think, beautiful. Okay, maybe go to the next level. So this is the last example. Let's consider 6 for 3 cases. We have such number, so we have to consider 106 gon. And expected periods 200, 1, 2. We can do it. And we have such variables and some relations. By some way, we figured out. So only reason we consider such a triangulation is to really formulate our Y system. And
how do you get from the continuous fraction to this beautiful picture?
Yeah, the general one is written in appendix. Actually, you know, we can do it generation-wide. So inside is first generation. This big one is a second generation we just described. We somehow subdivide this to make a third generation, and we do it next time we further subdivide. And there is some rule which is written in this appendix. There is some rule after all. But at this moment we didn't know how to do it. So somehow we found out this try and error. Again, this has two special axes. From this is a kind of quasi-symmetry. It is not a complete symmetry because we want to make a mutation. If it is symmetric, you can't do it. It's just stable. You can't do anything. But it is a kind of a little bit unstable, so you want to make a mutation, of course. And, well, if you make a tilt to your face a little, then you see there is another line which you make, if you make a mutation for those, it precisely gives you a reflection. Then you can combine these two things, then you can make a rotation movement, right? I mean, if you make a mutation here, then this one goes to this, and if you make a mutation, this goes to this, and so simultaneously, I mean, alternatively, you can make a rotation. So we have such, and so this is a 6th mutation, and so by this, after 2 steps, we have a 7 rotation by 17. Again, by some reason, these two are always coprime. And so you have to do this 100, this shift by 2, you have to do it 106 times. So add up period of 212. And it's important that they realize the Y system, or your target Y system. This is another demonstration. So now we are interested in this exceptional relation for this third generation. Once again, we are interested in this target variable 3, 1. It is written here. And it is mutated at u equal 1. So next time we have this factor. And once again, we make this. And we have some mutation point, but which is relevant to here. So this doesn't appear. Okay. But when this clock hit your things like this, you have some consequences. So this is another factor having here with right. This is a clockwise neighborhood. So we have such things. Again, we have something, nothing. But after 13, we have this one, and this is correspond to the third member of your second generation, and so on. Oops, so this is a 2, 2. Yes, this is 2, 1. And after that, it's interesting. We have two things, and the first one is inside of it is correspond to 3, 2. And this one is actually belong to your first generation. So your grand uncle will hit you. 1, 3. And this is a kind of exceptional one. And after that, this one, but still clockwise, so same factor. 13 here, hit it. 39. Oops. Okay. 41. And this is the last one. And after that, it hit to myself. And so it gives you a new number, new level. And so this is the Y system. So it completely explains what is Y system. Okay, so Sasha asked general construction. I can't explain this, but there is construction. So only from these numbers, this can be constructed. So Salvatore actually didn't write by hand, these things. He just make a program, and he just put those four numbers, and he created this automatically. For those numbers, you get this. You can see it, but fourth generation. Now, what about sine-Gordon? I concentrate on this reduced sine-Gordon. But sine-Gordon case, now we change only one thing. You have to put a puncture in the middle. Then you have to consider so-called tagged arc. And that's it. I mean, the only difference is the diagonals of the first generation. Others just remain the same. You just replace this. You just push it down a little, like this, and you add this one, and then make a mutation, then this inside just rotate, and explain this periodicity of sine-Gordon. So this is our proof of periodicity of sine-Gordon Y system. Now I still have some minutes to explain dilogarithm identity. So this is a general factor. So if you have a cluster algebra, which is, say, skew symmetric. And suppose we have some partial period of Y seed, like this. So we make a mutation and make after n step, you coming back to the original one, modular permutation of level. Then a general theorem proved by myself is follows. For any real positive evaluation of your initial Y variable, you just put inside and adding up, and you at your forward mutation point, divided these things, it gives some integer, regardless of your solution, where this number is a total number of this your mutated variable whose tropical sign is negative, where tropical sign is by definition the sign of the corresponding C vectors. So if once you know your period of Y systems is coming from the period of your cluster algebra, then we have such quality. But of course, still you have to calculate this number. And Tateo's conjecture say this number should be this one. And we can also prove this by analyzing the triangulation. So triangulation, again, is useful. Using the lamination technique, due to Fock and Goncharov and Formian thrust.
But in this formula, n is an integer.
Yes.
And in Tateo's formula, it doesn't look so.
Actually, this is integer. It turned out to be integer.
Huh?
Yeah. It doesn't look so, but it is integer. And so I now finish explaining this example. This is kind of a well-known example, but in this case, Tateo's conjecture tells me that the number is 20. I mean, the number of y variable mutated at during the period having a negative tropical sign is 20. And the lamination is the following. So here, this is the original triangulation. Lamination just rotated in a halfway, and this dotted line is lamination. And you put it for every lamination. So lamination is fixed, initial lamination. If there is for each this forward mutation point, you write this in a Z form, and if you laminate some lamination passing through in this way, then the tropical sign is plus. And if lamination go this vertical way, lamination is the tropical sign is minus. So, for example, this one, this is a Z shape, and this is passed by in this way, horizontal way. So this is at plus, and this is plus. But this one, for example, is passed by lamination in a vertical way, so it is minus. So we have minus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is for half period. But you can repeat this for one more times, and 10 times 2 is 20. And this is a proof of this number. And this is somehow known for this example, but this technique works for in general, and this proves the right dilogarithm identity part of Tateo's conjecture. Okay, I think we can finish. So this is a summary, the sine-Gordon y system, blah, blah, blah. But you notice that this is exactly the copy of my first pages. And you know that this is a periodicity. Thank you very much.
Technical question. So when you have this beautiful Tateo identity,
Yes.
you have denominators, P, A, Q, A. How
Yeah.
do you see, I mean, eventually you get an integer.
Yes.
How do you see the natural denominators? So what's their meaning? P, A, Q, A.
Well,
In your geometric picture, so
Yeah.
what's the meaning of this? Like system?
okay. First of all, this can be written in a little bit more simple way. And I forgot.
I can, so all the expression that goes from the summation sign over is actually the length. Can you look one of the features? One feature generation. Yes. So there is a center part, which is represents the first generation, and then there are other copies around that are the second generation and forth. The big number, the big summation, is just the length of the second generation. So for the classical type, it's 1, and then in that case, 17, and it goes forward. So you basically get it from the same continued fraction by forgetting the first term. And it's an integer on the nose.
Okay.
So you have to do some algebraic manipulation, but it's an integer on the nose.
So
Actually, I didn't understand at all. Anyway, it's okay.
In the classical RSOS Y system that you mentioned, it's interesting to find some constant solution for the Y system.
Yes, yes.
So do you have similar problems here?
So the question is, if you consider the RSS case and taken a constant solution along this time, it is actually represented by quantum dimension of Kirchhoff reciprocating modules. That's what you said. And the question is it possible to consider also for sine-Gordon model? Answer is no. I don't know. I'm sorry for short answer. I've never did it.
Even if you don't know the
Well,
you know that there exists
yeah.
one constant.
Oh, That should be yes. But the one point is I don't know the representation background of this Y system yet. There is a counterpart of T system, of course. Always for Y system, T system attached, and T system represent some decomposition. I mean, it's some relation of Grothendieck ring, but I don't know what is it. I suspect it is should be inside some category of finite dimensional module of quantum group SL2 at root of unity. But I'm not quite sure what really it is. So still, there is some mystery.
So this is extremely beautiful way to present this as G and RSG system. But as you explained in the beginning, this Y system is a very general physical kind of expectation for any massive to quantum.
That's right.
Theory.
Yeah.
So are there any other examples, where you can present as beautiful geometrically?
Yeah, the question is any other example of Y system having such things, and I never see it. If I see it, I think I can solve this problem more easily. Yeah.
Examples of Y systems, where you maybe not can solve this, but this phenomenon should be very general, right?
Well, usually, what we solve this Y system is using Coxeter kind of dynamics. So everything is input into Coxeter things. And of course, this A and D can be put also in Coxeter dynamics of very, very big Coxeter. But generally, the Coxeter root system is the best place to be put. But if you put this in a root system, it's too big, and we can't handle it. In this case, this triangulation somehow, I don't know the reason, but it worked very well. So I don't answer your question, but so.